Hey there, welcome to a video discussing section 4.2 implicit differentiations. We will do the first 3 pages in this video as part of homework number 18, due Thursday, November 12th. Sorry, just got a little distracted there. So anyway, let's talk about a circle here. So here we have a circle centered at 0, 0 with the radius of 3. So let's draw that right here. And let's use a different color to draw that circle. Oh, should not have done that, so let's undo it. So here we go. Not a bad looking circle. Well, I could do a little bit better there. That's better. Anyway, so the equation of the circle could be expressed like this. You might remember back in the day, the equation of a circle is this. Maybe in algebra 2 or pre-calculus, you guys discussed the equation of a circle where h and k is the center and r is the radius. Of course, the center is 0, 0, radius is 3. Plug them in for h, k, and r, you get x squared plus y squared equals 9. That's called an implicit equation. An explicit equation when you isolate y. So if I isolate y, that's real easy to do. You know, just move x squared to the side, square root both sides. When you square root, you got to put a plus or minus. So what's going to happen is that the top half would be y equals the positive square root of 9 minus x squared, whereas the bottom half would be y equals negative root 9 minus x squared. Now, suppose we want to find the slope of the tangent line at 2 comma negative root 5. Well, 2 comma negative root 5 would probably be somewhere over here, roughly, and there would be my tangent line. So I'm going to clearly use the bottom equation, not the positive square root. And if I take the derivative of that, that's going to be using chain rule here. If I take the derivative of the explicit equation with y being isolated. So remember, that's like saying negative parentheses 9 minus x squared raised to the negative half power. Move the negative half to the, sorry, positive 1/2 power, my bad. So move the 1/2 power to the front, and there's a negative there already. So negative 1/2, 9 minus x squared raised to the negative half. And then times the inside, which is negative 2x, using their chain rule. If you clean it up, the 2's cancel, negatives cancel, and you do have something raised to the negative half, which goes on the bottom. So you wind up getting just x over root 9 minus x squared. So I'm getting just that. Then, of course, if you plug 2 in, at x equals 2, the y value that goes with it is negative root 5, but we don't really have to worry about that. So that's just going to be 2 over root 9 minus 4, or 2 over root 5. And that's going to be the slope of this blue line over here. If I lose the little spotlight, this blue line, the slope will be 2 over root 5, which is roughly 0.8 to 0.9, so close enough, you know. Seems like we're pretty good there. And remember, derivative root x is 1 over 2 root x, and you can think of it as 1/2 times x to the negative half that we just did. So that's how we could do this explicitly, and that's what we've been doing all along. But what about implicit differentiation? So here's what's going on with implicit differentiation. Let me go and clear my screen and scroll down. So what if I took a derivative of both sides of the equation with respect to x and simply treated y as a differential function of x? So let's take a look at this here. I'm going to do d dx parentheses x squared plus y squared equals d dx of 9. So I'm basically applying the derivative operator to each side of the equation for the circle. Well, we know derivative 2x squared is easy. That's just, you know, 2x. Derivative of y squared is also, it's 2y. And derivative of 9 is easy. That's just a constant at 0. However, I also have to write this. And here's the reason why. Y is not x, right? It's just y. Now, we have x squared, and you take the derivative, of course it becomes 2x. And without realizing it, we've been doing this all along, x squared becomes 2x, so it's kind of like this, extra x, like this x squared is x times x. It seems like that, extra x kind of vanishes into the ether, but really what's happening is that this extra x latches on to that d there, and you wind up getting something that looks like this. That's truly what's happening when you take the derivative of x squared. It's like saying 2x, which we know is using the shortcut rules, but times dx over dx. And of course, those just cancel, so you just get 2x anyway. We've been actually doing this all along, we haven't realized it. So we have the derivative of y squared. It's going to be 2y, of course, using your shortcut rules, but then you got to say dy over dx, because you're doing this with respect to x. So you have to show that. You could also write y prime. Some people will write or 2y times y prime. That's fine too. But now what we're trying to do is we want to isolate. We want to isolate that. So then it becomes algebra at this point. And so if I do that, I'll do it down below here. So 2y is being multiplied to dy dx. The 2x will go over to the other side. It becomes negative 2x. If I divide by 2y, oops, meant to put dy dx. Dy dx is negative 2x over 2y. The 2's cancel. You get negative x over y. Now remember, we're doing this at 2 comma negative root 5. And when you see this there, that's what's implied. You plug in 2 for x and negative root 5 for y. So I'm getting negative 2 over negative root 5, which is 2 over root 5, which is what I got from the explicit way of differentiating. So this is implicit differentiation, because this, I guess you could say it's implied that y is a function of x. But because y is not x exactly, when you take a derivative of y squared, you say 2y, but then you got to say dy dx. And that's why we always have to be aware of the phrase with respect to x, and why we like using the dy over dx notation for this kind of type of problem. And I talked about that we would care more about that kind of notation, and we are. Let's try this again so you get the hang of it. Let's look at example 1 now. Example 1, you're asked to find dy dx. Now this is a really wacky equation. I'm not sure how that graph will look, but don't worry about it. The problem is that this is really hard to isolate y. I would not want you to do that, because I don't even know how you would even isolate y. You can collect all the terms of y on one side and do your best to isolate, but it's going to be almost impossible. Hard to isolate y. So instead, you do implicit differentiation. Here's how it's going to work. We take d dx of each side, d dx of x cubed plus y cubed, and d dx of 18xy. So you take derivative of x cubed, which is 3x squared. You take derivative of y cubed, which is 3y squared, times dy dx. And really, if you think about it, it's kind of like doing the chain rule, right? I mean, you have y cubed, you move the 3 to the front, drop the exponent by 1, and just multiply the derivative of the inside, which is y prime, or dy dx, right? And you can do the same thing with 3x squared also. When you have x cubed, derivative of x cubed is 3x squared times derivative of x. The derivative of x, of course, is 1, because we're doing this with respect to x anyway. Remember, it's dx over dx. But here, that's 3y squared times dy over dx. So this is implicit differentiation. On the other side, you're going to have to do a product rule. So I'll push 18 off to the side because it is a constant. So you take the derivative of x times y plus x times derivative of y. Again, you got 3x squared plus 3y squared times dy over dx equals 18. And we're doing the product with xy. Derivative of x is just 1, so 1 times y, plus x. Derivative of y is also 1, but you got to say dy over dx. Now you have to isolate dy over dx. So you're going to have to collect the terms with dy over dx. That's what we got to do. So now it's all algebra at this point. It's all algebra from here on out. No more calculus, all algebra. I'll do that algebra in red. So I'm going to distribute the 18 on the other side. 18y plus 18x dy dx. Put a little time symbol there. And you got 3x squared plus 3y squared times dy dx. So there's two terms to have dy dx. Let me get a highlighter out here for you. And we'll collect, it doesn't matter how you collect them on either side, I don't really care. They'll be all the same thing. Let's say I move this over here and the 3x squared over to the side. So now I got 3y squared times dy over dx minus 18x times dy over dx equals 18y minus 3x squared. Now I could factor out dy over dx on the left side. So dy over dx is pulled out. It's 3y squared minus 18x equals 18y minus 3. Ooh, that's not going to work because my screen's cracked. Equals 18y minus 3x squared. Oh, goodness. Try this again. 18y minus 3x squared on the right side there. So dy over dx is going to equal 18y minus 3x squared over 3y squared minus 18x. You could factor, I suppose, like factor out 3 and cross them off. I don't really care. Unfortunately, you can't use your calculator to verify this. You just have to have faith that you've done this correctly. So just be very mindful of all the algebra you're doing here. But that's the answer for that one. So that's example 1. Let's try this again on page 2. So let's look at example 2. Here x equals cosine y. Now if you want, you could isolate y and call it y equals inverse cosine of x, but I've not taught you how to do that yet. How to do the derivative inverse trig functions. Actually, we're going to do that in December after we come back from Thanksgiving break. Instead, we'll just do implicit differentiation. So we'll take derivative both sides with respect to x. So that's going to be 1, and that's going to be negative sine y. But then you got to take the derivative of y, which of course is dy dx. And dy dx, if you isolate it, is just negative 1 over sine y. And that's going to be your derivative. Sometimes your derivative could be in terms of y, not in terms of x. That's totally possible. So here are the steps. Take both sides, take derivative both sides with respect to x. If necessary, collect alternate dy dx on one side like we did in the previous example, and then factor it out at the end. Let's take a look at the next one here. Example 3, dy dx, find it if y minus 1 squared equals x, and then find the slopes at 4, 3 and 4, -1. There will be a Google form question kind of like this one, just so you know. I think it's number 4 in the Google form. Anyway, first of all, we kind of need to understand what's happening here. This is actually a sideways parabola, which I'll graph down here. I think the vertex is at 0, 1. If I plug 1 in for x, I think y would be 2 or 0. So it kind of looks like that. So this is a sideways parabola. And just remember, it is kind of like saying y minus 1 equals plus or minus root x, or y equals 1 plus or minus root x. So it is like graphing 2 square root functions at root x plus 1 and negative root x plus 1. So still the same thing. Root x plus 1 is that, and 1 minus root x is that one. So just a sideways parabola, that's what's going on there. But anyway, let's do this implicitly. So if I take derivative both sides here, you move the 2 to the front, 2y minus 1 raised to the 1 power, times derivative of the inside. The derivative of y minus 1 is just 1, but times dy dx. Remember, y minus 1, if I do that derivative, that's going to be 1, but then you got to say dy dx. And derivative of 1, of course, is 0. So it's just dy dx. So we have, again, 2 to the front, drop the exponent by 1. Actually, I don't really need to show that anymore. But then the derivative of the inside of y minus 1 prime, you're just going to get dy dx. And actually, let me just backtrack a little bit, just so you know exactly what I'm doing. So again, chain rule, but that's really going to be, again, 2 parentheses y minus 1 times dy dx. And we'll do that in red again for color coordination. On the other side, that's just easy. That's just plain old 1. Remember, you don't have to do that. You could say times dx or dx if you want, but it's redundant. Just say just 1 straight up. And again, our goal is to isolate dy dx. So dy dx is 1 over 2 parentheses y minus 1. Now, let's find the slope of the tangent line at 4, 3 and 4, -1. We don't really have to plug anything in for x because it's right in terms of y. So for 4, 3, you just plug in 3 for y. That's 1 over 2 times 3 minus 1. That's going to be 1/4, which kind of makes sense. At 4, 3, it looks like that does have a slope of 1/4. And then this one here, we do 1 over 2 -1 minus 1, which is -1/4. So at 4, -1 is over here somewhere, and that does look like a negative slope of -1/4. So I feel good about this. That's example 3. And again, this is all very mechanical, like everything we've done so far in this unit. Let's look at example 4 now. Find the equation of the tangent line to the ellipse. This is a wacky ellipse at -1, -2. I think it's kind of like a slanted ellipse, but let's not worry about that. We don't have to worry about how these look graphically. Plus, it's going to be impossible to isolate y. So again, take derivative of this with respect to x. I know I haven't written that all the time, but I'll just do it here anyway. So it's going to be 2x minus, and I'll kind of do this here because I'll have to do that kind of separately, plus 2y, but you got to say dy dx. And the other side is just a constant. That's going to be equal 0. Now for xy prime, that's a separate problem within itself. So it's going to be x prime times y plus x times y prime. X prime is 1, so 1 times y plus x. And y prime is 1, but you got to say dy dx. Now let's bring it back into the mix. 2x minus parentheses y plus x times dy dx. Let's do that in red. Again, very mechanical. We'll practice this a lot on class on Thursday and Tuesday of next week. And there'll be lots of homework on it too. Plus 2y times dy dx equals 0. So now we're going to isolate dy dx. So I'll move the 2x over to the other side. It's kind of all lonely. So it'll be -2x over here. Actually, let me backtrack a little bit. Let's just do with that minus. And that parenthesis 2x minus y minus x dy dx. I won't color coordinate anymore. Plus 2y dy dx equals 0. But again, I'll use a highlighter. You want to isolate the dy dx. So anything that doesn't have dy dx goes to the other side. So now it becomes -2x plus y on the right side because those guys moved over, right? Those guys moved over to the right side. Factor out dy dx, and I'll have -x plus 2y. Now dy dx can be isolated. It'll be -2x plus y over -x plus 2y. Nothing can cancel here. Just leave it as is. And that's going to be your derivative. Now, you may have it the other way around too. You may have -y plus 2x and -2y plus x. That's if you decide to put the dy over dx on the right side and everything else on the left side that didn't have dy over dx. That could happen too. It's totally the same thing because you could factor a negative from both top and bottom and still get the same thing that I got down below, the bottom page too. So they're all the same thing. Don't worry if your signs are opposite of what I get or get from the homework. But then we want the equation of the tangent line, so let me do that in black. So remember, tangent line y minus y1 equals m times x minus x1. So it's y minus 2 equals mx plus 1, because you're doing x minus -1. Your slope, you're going to plug in -1 for x and 2 for y. So -2 times -1 plus 2 all over -1 plus 2 times 2. So it becomes 2 plus 2 up top, 1 plus 4 on the bottom. You get 4/5 as our slope. So our slope is 4/5. So the equation of tangent line is y minus 2 equals 4/5 x plus 1. That's example 4. Let's move on to the third page, the final page of this video. So So unlike examples 1 to 3, the last problem did not ask us to find an expression for dy over dx, but I did it anyway. So this means that we could have worked as follows after we got to the third line. So for example, one of my problems, let's take a look at example 1. Wait, hold on a sec. Oh, actually, sorry. Let's take a look at example 4 again. So for example 4, remember one of our steps was this. We had 2x minus, and then in brackets we had x, or we had y plus x times dy dx plus 2y times dy dx equals 0. This was from example 4. Remember, that was one of our steps we just had. So since they didn't really ask us for an expression, we just needed the slope, which is of course the value of dy over dx, just needed slope. So I suppose I could have just plugged in -1 for x and 2 for y. Again, 2 for y. And you could have just done that too if you wanted to. -2 minus 2 minus -1 becomes plus dy dx plus 4 dy dx. I want to make sure I'm doing everything correctly here. I think so. Yes, Sam. Equals 0. So -2 minus 2 is -4. Move that to the other side becomes +4, and you have 5 dy dx. So dy over dx is 4/5. So you kind of done it that way also if you so desired. So if you're not asked to explicitly find this derivative, which is kind of weird to use the word explicitly, I mean, you're not asked directly to find dy over dx in terms of x, y, and only need its value of a particular value of x, like the slope of a tangent line, then you can just substitute for x, y as soon as you've differentiated both sides and removed all parentheses. So you could do that also. Or before you remove parentheses, I guess you could, distribute, but after you do a derivative. Okay. Now we could actually graph this in our calculator. I mean, we could do that. You have to be a little creative. It doesn't work all the time, just so you know. Like for example, I don't think this would have worked for example 1. But if we do this, you could say y squared minus x times y, and move the 7 over to the other side, plus parentheses x squared minus 7 equals 0. Think of this as a quadratic. Think of this as a quadratic where it's going to be like this. Oh, my stat stopped working. So where your a is 1, your b is -x, and your c is x squared minus 7. So think of it as a quadratic in terms of y. So if you do quad form, so instead of x, we'll say y because we're just in terms of y. So y equals -b, which will be -x, plus or minus b squared. So you're squaring -x, minus 4ac. So 4 times 1 times x squared minus 7, all over 2a. So you could actually isolate y in this case, but you had to get very cunning or very creative here, which would be an x squared minus 4x squared plus 28 all over 2. You can clean up a little bit inside the radical and just kind of graph all that. Yeah, just be a little messy here. And it's plus or minus, so what you actually have to do is x over 2 plus all that junk, and x over 2 minus all that junk. And you still have to divide the radical by 2. I suppose you could have done that and then graph your tangent line just to see if it's actually touching it there. So there's a way you could actually graph this, just see how it looks. You can also do it in Desmos too. I think Desmos would actually do that nicely for you. And then you could just look at the particular point we're looking at, which was at -1, 2, and kind of see if the slope would be about 4/5. So you could do that also. So I'll recap this when we meet again on Thursday. And that concludes the video here.